So, hi, hello. Welcome to section number 5 for Chem E-27x. Woot woot woot. We are continuing Unit 2, where we are in cofactor land, where we are learning who are the players, what can they do chemically, what are some biological examples of them. Last time in section 4, we learned about ATP and SAM. And then in lecture 5, two new cofactors, NAD and FAD, were introduced. So the goal of today is just going to be to try to do kind of a roundup of that and do some practice. We'll start off with reviewing a little bit on redox. We won't spend much time on it. Then we'll go into NAD structure and function, and then some examples with NAD, followed by FAD structure and overview, and then the first type of FAD mechanisms that you'll learn, which are the reductases. So, first up, a review of redox. So, in a very, very general sense, when you were in Gen Chem, you learned about redox reactions, reduction and oxidation, and you probably learned like oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. And a lot of what we are talking about with oxidation reduction in like organic chemistry or biochemistry has to do with like losing electrons. Like, what does that properly mean? Because we still like satisfy the octet rule and everything. And typically, it has to do with electronegativity and like the amount that these atoms want to hold electrons closer to them. So, imagine we have a covalent bond and we are going to kind of split it. Who do the electrons go with? Well, they go with whoever's most electronegative. So in this case, the oxygen's more electronegative than carbon. Oxygen would take its electrons and the carbon would have a positive charge. And so, because this is what would happen if we split the bond, we say that carbon is oxidized here relative to like methane. So carbon has less ownership of electrons around it because it's connected to an electronegative atom. So in Gen Chem, you were doing formal oxidation states. So this was like the degree of oxidation where you were like oxidizing all of the bonds, seeing who the electrons went with, and then calculating a charge. That is a little overkill for what we need for organic chemistry. For organic chemistry, we use a formalism that's centered around carbon oxidation, and we call it the oxidation level. And so the oxidation level, the shortcut for it is the number of bonds that a carbon has to electronegative elements. So at the top we have the carbonate oxidation level 4. Here carbon has 4 bonds to electronegative things. Then we have the CAD oxidation level 3, the aldehyde oxidation level 2, the alcohol oxidation level 1, and then the alkane oxidation level 0, I suppose. And so as we go up from level 0 to level 4, we are doing oxidation, and then as we go down, we are doing reductions. And the reason why we like often care a lot about redox reactions is functional groups at the same redox level typically undergo similar reactions. So that's why we talk about like CAD chemistry as being like the chemistry that all of these functional groups do and how we like interconvert between them because they do very similar reactions. We also can talk about this, and this isn't really a formalism that we used in 17, but these are all 2 electron oxidations or reductions. And it's because there are 2 electrons in this bond that would go with the electronegative element if the bond broke. So like if you went from an alcohol to a ketone here, that would be a 2 electron oxidation, and the other way would be a 2 electron reduction. The reason why we are kind of bringing in this notation of it's a 2 electron oxidation or reduction is because we are going to see examples that are 1 electron oxidation reductions. So we're just kind of like planting that seed for now. Doing redox reactions in Chem 17, our main oxidizer was chromium trioxide, CrO3, and our main reducing agents were lithium hydride and sodium borohydride. And we didn't give you a mechanism for the oxidation with a chromium, just because the metals mechanisms are a little bit more complicated. But we did give you a mechanism here for the reductions with lithium aluminum hydride or sodium borohydride. And the core idea here is the hydrogen with its electrons, which we call a hydride, went and attacked a carbonyl. And that's how we did the reduction. So these were our main players in organic chemistry, like lab organic chemistry. And in biochemistry, Chem 27, our main players that are doing redox are NAD and FAD. And so we will get into that with the sections today, and also I believe in the next lecture we're going to be doing more with FAD. But before we move on, just to do like a little practice on redox, let's go through each of these reactions and label each of the reactions as either an oxidation or a reduction, and then label it as either a 1 electron or 2 electron oxidation or reduction. So, first up, I'm going to do this. Always we are playing a spot the difference game. So here I see that we have a carboxylic acid, and then we have an aldehyde. So we've moved from oxidation level 3 to oxidation level 2. So we did a reduction since we moved down, and this is a 2 electron reduction. Most of these are going to be 2 electron. Over here, going from an aldehyde to an alcohol, we went from oxidation level 2 to 1, so it's a reduction, also 2 electrons. And then finally, over here, from alcohol to alkane, we do one final reduction, that's 2 electrons. So this one just kind of took us down from 3 to 2 to 1 to 0 down here for our oxidation level. For the second column, we had an OH that was turned into a Br. Is that going to be a redox reaction? Well, the carbon here is connected to one electronegative element, either the O or the Br. And it's not being connected to more electronegative elements. So this one would not be a redox reaction. Okay, then we are going from the imine to a nitrile over here. So here that carbon is getting one more bond to an electronegative element. And if we're increasing our bonds to electronegative elements, here we went from 2 to 3, we have an oxidation, a 2 electron oxidation, because we go up in oxidation level. Then finally, we're going from this nitrile to an amide down here. And if we look at this carbon, it has a double bond to oxygen, and then it has a single bond to nitrogen. And so it has 3 bonds still. So this is not a redox reaction. We did not change. Sorry, I got like distracted by something on my monitor. It looked very weird. I think it's the new like Apple like glass thing. I was like, oh, something's going on. But yes, so nitrile and amide are both in that CAD family at oxidation level 3. This one up here, we go from oxidation level 0 to a bond with SH, oxidation level 1. So we increase oxidation level, this is an oxidation, and it's 2 electrons. Final example, which is the hardest one. Here, we are going from this thing to this thing. So to help us out here, let's look a little bit at what the oxidation level of this is by thinking about this single bond. In this single bond, the electrons are shared between 2 oxygens, and neither one is more electronegative. And so if we tried that exercise of splitting the bond and see where the electrons go, the electrons are actually going to go 1 with each of them. And that's a little weird. So this is sometimes called single bond resonance, which you don't need to worry about all this. This is like, again, a little bit new, is like a preview of something you're going to see next time. So if it's like crazy out there right now, that's okay. But we can think about these electrons as being equally shared, where like this oxygen over here takes 1 of the electrons in the bond, And this oxygen over here takes another electron that was in the bond. So with that, if we look at these, the kind of starting materials versus the products, we see this RO dot stays the same. That is not being oxidized or reduced. But this oxygen over here is going from this oxidation, where it has 7 electrons around it, to you have 3 full lone pairs, and you have a bond with H. So you have 8 electrons around it. So what the reaction here did, which I'll put in purple, is it adds 1 more electron and it adds an H. And that's going to be a 1 electron reduction. And it's because this oxygen is owning more electrons around it. Remember, hydrogens are essentially just a proton, not very electronegative at all. And so the real owner of the electrons in this OH bond would be the oxygen here. Again, if this one is a little bit confusing for right now, no worries. You will get more with these single electron things when we do the second part of FAD. And I think this coming lecture. I could be totally wrong. But any questions on this redox practice 1? My fun fact on this is a practice I stole directly from the 2017 version of Chem 27 when I took it as a student. I didn't love the first practice in the workshop problems for this week, and so I was like, let's do some practice with just like recognizing oxidation states. Yeah. Cool. Well, if there are no questions on this one, let's go and meet NAD. So, who is she? NAD plus, her legal name, her government name is nicotinamide adenine dinucleotide. Dinucleotide here coming from like 2 nucleotides, which means a sugar, a phosphate, and a nitrogenous base. So we can see those 2 nucleotides here and here. And it's kind of funky, like there's a lot going on, and so that's why I like to do these kind of color-coded labeling of structures. So we have adenine, ribose, and a phosphate, which we saw previously. This is AMP. We can group it together like that. And then the phosphate is connected to another phosphate, ribose, and now this new thing. So this new thing is going to be the business end of NAD, and all of this other junk we are just going to abbreviate. We are going to do like a line and a squiggle. So this business end is a little pyridinium ring and an amide on it. And this is called nicotinamide. It's related to vitamin B3. So if you've seen in the grocery store the vitamin B3 supplements, niacin is that pyridinium, or pyridine here, with a carboxylate on it. And then that is turned into nicotinamide, and then that's added on to all of this like nucleotide nonsense. So we have kind of 2 flavors of nicotinamide stuff. We have NAD and NADP, and the only difference is whether or not this is an OH in NAD, or if we put an extra phosphate group on it in NADP. And really, it's just a tagging system for cells to say, hey, what are we using this cofactor for? NAD alone is typically used for energy utilization, so things like metabolism, whereas NADP is typically used for biosynthesis. Wait, when I said metabolism, that's too broad. Energy utilization, I'm like doubting myself all the time here. Let me double check one thing to make sure I didn't write down something wrong. Yeah, I think I'm going to erase this word catabolism here, because I typically think of NADP as associated with anabolism, building things up. Like NADP is used in fatty acid synthesis. It's used in the pentose phosphate pathway. So I typically think about NADP as like building something up, whereas NAD is more about utilizing energy and typically breaking things down. Yes. Now, NAD is kinetically stable, like ATP. So she is a free agent. She is like wandering around the cytosol, living her life. And she's not going to be reactive until she is in an enzyme active site. And then that is going to be able to let it do like the chemistry that we normally see. So kinetically stable, it's not going to react on its own without being in an enzyme. So let's look at what it is doing. So I said its core function here is redox, and it's essentially nature's version of both chromium and LAH. It is going to be doing both oxidations and reductions. So our general mechanism here looks like this. So we have our abbreviated form of NAD, and we know when we have a benzene-like ring here, an aromatic ring, there's only one hydrogen on each of the substituents here that's unsubstituted. So what happens is NAD is nature's oxidizing agent. It is available to accept a hydride from some molecule that you're trying to oxidize. So for example, here is an alcohol. What would happen is we are going to try to turn this alcohol into a carbonyl. So we need to make a double bond here, CO, but this carbon has too many bonds. And so it's going to push off a hydride. And we need somewhere for that hydride to land, which we typically call a hydride sink, where we push hydrides off. And so the hydride sink that we use is NAD with a positive charge down here. So a base comes along, deprotonates the H on the alcohol. This folds in, makes the carbon-oxygen double bond, and then an arrow goes from the bond of the CH here, so that's the hydrogen traveling with its electrons, to the top carbon of our NAD. Now, once it's on the NAD, we need to get rid of one of the bonds here. The only one that can easily move is the pi bond, and so we fold down and go all the way to the nitrogen with a positive charge. And so it's kind of like a little bit beautiful to like see the flow of electrons here going from where you are taking electrons, the base here that starts it all off, and the ultimate sink of where the electrons get pushed onto this nitrogen. So once we do that, our structure has changed here for NADH. So NADH, we no longer have a positive charge at the bottom because we pushed electrons over to the nitrogen, and we have two hydrogens up top here. So if we wanted to do the reverse of this reaction, we totally can. NADH can act as a reducing agent and essentially be a source of hydrides, like if we had like aluminum hydride, like this, where the bond would just go and attack a carbonyl. So it is a hydride source, kind of like LAH. So we would essentially just undo all the arrows. We would start pushing from the bottom nitrogen. And when we do this, interestingly, this ring started off aromatic, but when it accepted electrons, it was not aromatic anymore. And so it looks like we just have our double bonds kind of vertically on the sides, but we have very specifically an sp3 hybridized carbon. So that is not aromatic. So with this, there's kind of a trade-off going on here. Aromaticity is very stabilizing. The molecule wants to be aromatic, but if it's aromatic, it's going to have a positive charge. So it's not neutral. And then here, if it's neutral, it's not aromatic. And so it's kind of not amazingly happy either way. And so it can do either of them. It can do this aromatic version where it has only one H, or it can accept another H and be the non-aromatic version. But back to the mechanism. So we push up to restore aromaticity. Then our hydride will go and attack our carbonyl. And then from there, we will grab a hydrogen from some acid, general acid. So these you are going to be doing over and over. You are going to see a lot in this unit. And we will get practice with it in a moment. Any questions about like who she is, what she is doing so far with NAD? It's a quiet section today. Have the exam 1 scores destroyed morale? Maybe I should have looked at the exam 1 scores. I'm sorry. Okay. Well, one key fact to know about NAD is NAD does stereo-specific reactions. So what that means is there are 2 hydrogens on this NADH here, right? One that's on a wedge, which we can consider the top face of the molecule. One on the dash, which we can consider the bottom face of the NAD structure. But all of these other ones are aromatic. They're in the same plane. So it would be kind of like we had a sheet of paper with all the things in the same plane, and we have one H going out of the page and one H going under the page. Because of how enzymes hold NAD and NADH and very specific conformations in the active site, it is going to control it so only one of those faces actually reacts with the molecule. So in this example here from ADH, alcohol dehydrogenase, the molecule is holding NAD over here, and if this is our like little amide, we know that the NAD hydrogen top point that does the reaction is this one up here. And then we have our substrate over here, a methyl, and then this is going to be a carbonyl. Or sorry, no, this is still an alcohol. We would have this OH. And then here we would have like a hydrogen and a deuterium that's not shown on here. They did an isotope labeling experiment to figure out, oh, okay, I'm only getting one stereoisomer. Is that proven? Essentially, if there was a hydrogen here on this molecule, then when we added the other hydrogen, it wouldn't be a stereocenter, so we can't really say anything about the stereochemistry. So what they did was they swapped out one of the hydrogens for deuterium, and now this is connected to 4 different things, so she's a stereocenter. In this mechanism, because NAD is held in this specific conformation, and because the substrate is held above it, only this top face hydrogen goes and interacts and attacks. It controls exactly which face of the substrate that we are attacking, and so in this case we only get the S stereoisomer. We don't get the enantiomer of this, the R1, at all. And again, I think it's just one thing that we had to consider in 17 in a beaker with like lithium aluminum hydride and sodium borohydride is when we did our reductions, this, if we like drew it out with a true stereocenter, like an OH and an H, this would form like a racemic mixture of the R and the S version, because this has no control over which face reacts. It's literally like just bumping into each other in a beaker. Whereas enzymes are the Da Vinci surgery robots. They have all the control over how everything is positioned. So I think that was a lot of words and me talking for the simple like statement that it makes one stereoisomer. Okay, we have practice 2. So practice 2 down here shows ADH utilizing an NADH cofactor and converting this substrate over here into this product. And for a minute there I was like, I just copy and pasted. They are the same molecule. But they are not. What has changed? Well, this carbonyl got reduced over here to this alcohol. So we did a reduction from oxidation level 2 to oxidation level 1 here. Let's draw out our mechanism. So in our mechanism, what I typically do is I start drawing a benzene and I just leave space at the bottom for nitrogen. I connect it down and then do my little squiggle NADH. And if we're starting with NADH, we know that we need to start with 2 hydrogens up top. Also in this version where we have 2 hydrogens up top, we are going to have just bonds on the left and right side. We're not going to be fully aromatic yet. I was like, am I going to draw this whole thing again? I'm just going to copy and paste it. Okay, so we need to get one of these hydrides onto this carbonyl. So we start by pushing from this bottom nitrogen. We are going to restore aromaticity. Then we need to kick off our hydride. It's going to come up and attack the carbonyl. And then we are going to grab an H from a general acid here. And I just wrote it as BH plus instead of HA, but either one works. And then from here, we get straight to our product, actually. And the thing that came out is NAD+, which I will draw that structure just for practice. So again, I like trying to draw like hexagon benzene, put a nitrogen at the bottom. For NAD+, we do the full aromaticity, and we have the positive charge on the nitrogen. And, ooh, I didn't draw my little amide boy, NH2 on the side. There we go. Much better. Much better. So, the NAD mechanism, to me, isn't super bad, mostly because it's this one-step mechanism. The thing that's a little bit weird is it's a lot of arrows for one step. And a lot of these arrows kind of follow similar arrows that you've probably seen. Like this is attacking a carbonyl. This is a protonation. And these are kind of resonance arrows. So it kind of combines a lot here. 1, 2, 3, 4, 5 arrows in one step. But at least it's not super big multi-step. It's also, at least we don't have to draw active site catalytic triads over and over again. So that's good. So now it says which face of the substrate was NAD accessible. Well, if we look at it, we see we get this specific enantiomer of the product, and the H was added on a wedge. Ooh. So if the H was added on a wedge, then we added to the top face. Basically, we approached this molecule from in front of the page, from kind of where our perspective is compared to the page. It attacked from the front rather than behind. And that's why our H is on a wedge. Now, the other thing it asks us to explain is what is stereospecific versus stereoselective? So stereospecific is one stereoisomer product. Stereospecific. I'm specifically making this. Stereoselective means produces multiple stereoisomers but favors one. So all the NAD reactions, to be explicit, are stereospecific. We are never going to get a mixture and like it has a preference for one over the other. It's always just going to be exactly one product. Cool. Any questions on practice 2? Then let's keep going. So that was NAD, structure and function. That's kind of the intro. And then we have a few kind of classic examples that you spend a little bit more time in lecture on. And one is HMG-CoA reductase, which we'll talk about now. The other one is proline biosynthesis, which was like a big Poly-V question. I think that that's like a beautiful... Oh, it's saying I'm giving a thumbs up. Why does it keep doing that? Okay, it went away. Proline biosynthesis, I think, is a beautiful example of ATP and NAD cofactors at work. And I did not like fully do all the notes of this. I ran out of time, and so I just drew kind of the framework of it. And maybe if we have time at the end, we'll go back and add some mechanism here. Specifically, I think it would be helpful to talk about this step where it goes and forms an imine. And that's going to be a nice reminder from Chem E-17 or S-17. But these are the two big examples that you saw of NAD reactions in class. And then we're going to do another practice with an NAD mechanism that's a little bit weirder. So, HMG-CoA reductase. Who is she? What's going on? So HMG-CoA is this girl. This girl does have stereochemistry. And I'm just realizing I added an H over here when that should just straight up be a methyl. My bad. So, she has a stereocenter over here, wedge, and dash. HMG-CoA is 3-hydroxy, 3-methyl gluteryl CoA, something like that. That's a mouthful. We just call it HMG-CoA. And HMG-CoA is converted into this molecule mevalonate. Now, as we do this conversion, we are going from here, a +3 oxidation level, or oxidation level of 3, to oxidation level of 1. So we did a reduction, and we did a 4-electron reduction. So if we were doing this with like NADs or NADHs, we would need to use 2 equivalents in order to go from oxidation level 3 to 1. Now, mevalonate is a main intermediate in making cholesterol, and it has this whole mevalonate pathway that we'll talk about in a minute. But let's just talk about kind of accomplishing this chemical goal of doing these multiple reductions together. So a recap strategy page here is we are going to reduce this thioester to the carbonyl becomes an alcohol over here, and we still have the sulfur. And we're going to do it with one equivalent of NADP. What am I doing? I'm just making a bunch of mistakes. We're using NADPH, not NADP+. And technically I can blame past Colton, because this is the first one where I had like a rough draft lesson plan from when I was tutoring this in like 2022, I guess. So I was able to kind of copy a good degree of it from way back then. But these are NADPHs, not NADP+. Apologies. I will try to correct this real quick. And we know that whenever we're doing reductions, we need a source of hydride, so we need to have the H already on our nicotinamide cofactor. So our strategy is we reduce the thioester to an alcohol and a sulfur with a first equivalent of NADPH. Then we are going to do a lone pair push and kick off our S-CoA with a base. And then finally, we are going to reduce the aldehyde that's formed into an alcohol. So we do the NAD mechanism and push the hydride up onto the carbonyl here. Then we are still here, or not still here. We started at oxidation level 3. Now we are at oxidation level 2. We've done one of our reductions. And the thing that gets kicked off is NADP+. Boop. 。 Then, once we are here, and I'm catching another error, I think that this is going to grab a hydrogen from some general acid. We are doing a lone pair push. From the alcohol here, we're going to reform a carbonyl. So a base removes the hydrogen, reform a carbonyl. And then we are going to take the electrons in this bond from the sulfur and grab an H. And so what we get kicked off is a neutral enzyme CoA, which we are going to see more of CoA pop up as we get into more metabolism and things like that. Boop. Then from that, we are at an aldehyde level here, and we are trying to get to just an alcohol here on the end. So in order to do that, we use our second equivalent of NADPH. We do our standard NAD mechanism attack, and we take it from a carbonyl here just straight up to an alcohol. So again, a kind of classic example of NAD chemistry. You get to see it twice in action doing two reductions. This we said is part of the mevalonate pathway, which makes cholesterol. And this HMG-CoA reductase is, I believe, the rate-limiting step in making cholesterol. And so if you have high cholesterol from like a medical standpoint, what do you want to do to HMG-CoA reductase? Well, you want to shut her down. Enter the statins as a class of drugs, where the classic example is Lipitor here. So Lipitor has kind of two main parts to it. One is this common kind of side chain that you see in a lot of statin structures that resembles HMG-CoA, which I've just drawn the HMG-CoA structure down here for reference. So this bit with like a oxidation level 3, oxidation level 1 and 1 mimics oxidation level 3, oxidation level 1, and oxidation level 2 here. And in fact, by doing it at oxidation level 1 here and making it an alcohol, it's actually resembling the transition state of the enzyme a little bit more than the original substrate. And so it can outcompete via the Pauling principle. So we have this common side chain that's going to be the transition state mimic. And then the other part that we have is this big like hydrophobic boy. So we have these phenyl groups, we have this aromatic ring, lots of like non-polar junk. And this is kind of mimicking the CoA part. And in fact, they've designed and engineered this part of the molecule so that it binds to the hydrophobic residues in the active site even better than HMG-CoA. And here it's also, the binding is being driven by the hydrophobic effect. So it's kind of kicking out ordered water and letting that water be free and not associated around this inhibitor, huge like hydrophobic residue. So this is kind of a classic example of something that is going to inhibit our HMG-CoA reductase by binding in the active site as a competitive inhibitor. It's not going to be covalent inhibition. But yes, great example of it. Proline, we are going to skip for now. Like we said, it's going from glutamate to proline. So prolines are made from glutamate residues in terms of amino acid anabolism, building it. And it's beautiful as an example because we get to see the imine reaction, we get to have two NAD steps, and we get to see ATP. So it does a lot of great work in bringing together all the chemistry that you've seen so far. But let's try another MAD mechanism together here for practice number 3. So, the background. Some bacteria have involved ADH-like enzymes that catalyze redox reactions of nitrogen functional groups, such as nitro groups. Here is an example shown below where NADH is used to do a reduction of nitrobenzene all the way over to this molecule. So we are not reducing carbon anymore. That's kind of interesting. As a reminder, we have nitro groups look like double bond to O and a single bond to O. And the nitrogen has 4 bonds, so it has a positive charge. So we can think of this as essentially being kind of like if the nitrogen was a carbon here, something at oxidation level 3. Because we have 3 bonds to the more electronegative oxygen. And then in our product down here, we only have 1 bond to an electronegative element to oxygen. And so we are doing 2 reductions. So again, this one looks kind of different, but it should still be the same kind of core setup. So let's try it out. So I start off with my NADH. And our mechanism here, we are going to push from the bottom nitrogen, restore aromaticity, and the hydride is going to go and tack this kind of nitrogen carbonyl looking thing. And then I shouldn't just push up to the O, I should grab a hydrogen from some general acid. So now, in our next step, we would have OH, O minus, and we've added an H. So our nitrogen still has a positive charge on it. And it looks like what we need to do in order to finish this step to get to this intermediate here is we need to kick off a water and we need to form a carbonyl. So maybe kick off water, form nitrogen oxygen double bond carbonyl like thing, and we need to remove a hydrogen from the nitrogen. So those are kind of our concrete chemical goals here. So what that's going to look like is we are going to push down, form a carbonyl, or again, it's not a carbon, but nitrogen oxygen double bond. Then we are going to kick off this OH, and it's going to grab an H from, again, some general acid. Now, when we do that, we are going to have this, right? So it is a nitrogen, and it still has 4 bonds, even with this carbonyl. And really, to get to the product that we want, we just have to do a deprotonation, right? Well, remember, we can just abbreviate that by putting a proton transfer over the arrow here. And that proton transfer, I'll kind of color code it to help keep track of it. That is going to let us just erase this hydrogen and go straight to what our product looks like for this intermediate structure. I also was a bad organic chemist and I forgot to draw my NAD, so I will draw my NAD here. And she is just kind of a byproduct after we've used our NADH. So we've made it to our middle point, and then to get to the end, we just need to do the same exact process. So at this point, I will copy and paste. Our hydride now attacks the nitrogen, and we go and protonate our carbonyl. Then, I believe we are at our product structure. So our nitrogen, we've added an H onto it. Our NO double bond becomes an OH on the nitrogen. And we form an NAD, a second NAD. Slide. Also, if you didn't do this as a proton transfer, you totally could have shown it as a separate deprotonation step. That would get full points. Cool. So, again, this is kind of a mechanism similar to the HMG-CoA reductase, where we are using two equivalents of our reducing version of nicotinamide cofactors. But we're doing it on a nitrogen. Ooh. Any questions on this before we move on from NAD? It's so quiet. I'm like, ma'am, they're really angry. Exam one was, I hope exam one wasn't horrible, but are people okay? Are there signs of life? I see.
Wait, Connor,
Yeah,
you have a question. Sorry, I was
please.
gonna ask, should there be a formal charge on the nitrogen in the pyridine ring for NAD plus down here? Or am
Yes,
I
there
bugging?
should. And I put the plus on the little label, but I didn't actually put it on the nitrogen. That would have been minus zero .5 and minus zero .5 for me. Nickel and dime with the formal charges. Nickel and dime. Thanks for catching. Okay. So, this is NAD land. She's not too bad. FAD land. It's a little bit worse. It's a little bit worse because it's a little bit more complicated and it's a little bit more options for what you can do. NAD and NADH are kind of doing the same thing every time. Whereas Flavin, you don't really know what's up with her. You know, you have to look at the context, read the room, see who's around. But let's start off with kind of structure function FAD and just meet our main players here. So meet the flavins. So what we're going to start off with is this big molecule down here. This is riboflavin, vitamin B2. And riboflavin here is made up of two things. One is a deconstructed ribose, hence ribo. And then this section is called a flavin. And the flavin includes an isoalloxazine ring, which honestly, I thought I knew what that was, but I'm going to Google. I thought it was the whole 3-ring structure. And it is. It is. So we call this whole ring structure isoalloxazine. And then that became a mouthful, and so I think we started calling it flavin. That's like my best understanding of it. But this is our business end of the molecule here. And then the rest above it, we don't care about. We just abbreviate with just a squiggle up top. But riboflavin, we hardly ever see on its own. This is kind of like the thing that you eat in your like vitamin or whatever. And typically it's packaged into one of two different forms. So if we replace this OH with 2 phosphates and ribose and adenine, this becomes FAD, flavin adenine dinucleotide. And it's a dinucleotide because we see, oh, okay, we have an AMP subunit here, adenosine, ribose, and phosphate. And then we have another setup here of a nitrogenous base with our flavin, a sugar, even though it's deconstructed, and a phosphate. And so it's like we have 2 nucleotides glued together, dinucleotide. Or if this OH is just a phosphate group, then this is what we call FMN, flavin mononucleotide, because we would have a phosphate, sugar, nitrogenous base, single nucleotide unit. For the purposes of our class, FAD and FAM are pretty much interchangeable. Interchangeable. And broadly, we call these class of cofactors flavins. Some notes about flavins. Flavins are unstable in air. Me too, girl. They are O2 reactive. And because they are O2 reactive, they are not free agents. You are not going to see FAD, FADH2 just floating around in the cytosol. She is bound in an enzyme. And it might not be a covalent bind to the enzyme, but it is so tightly bound with IMFs that it's like functionally like permanently there. So she is not floating around. Also, this isoalloxazine ring here, she has a lot of dang resonance. She is a big, huge little aromatic ring with 2, 4, 6, 8, 10, 12, 14. Is that right? 14 pi electrons? Is that a Huckel number? 4n plus 2? It is. That's going to be 3 times 4 plus 2. So that is an aromatic number of electrons. This whole ring is aromatic and super delocalized. And a consequence of that, of having so much resonance here and aromaticity, is that we are going to be able to do 2 electron reactions, just like NAD, but we are also going to be able to do 1 electron reactions with radicals. And that is going to be the more complicated side of flavin, which we are not doing today. So we are going to stick with 2 electron reductions and oxidations today. But one thing, you are going to be drawing this business end of FAD over and over and over. And like, it is honestly going to become a rate limiting step of your work on a reaction. So like, especially in exams when you're in time conditions, you want to be able to draw this quickly. Just like you wanted to be able to draw the catalytic triad quickly. And just, I'm going to tell you like my little way of conceptualizing it. So I always think about it as 3 rings. So we have this first ring, this second ring, and third ring. And honestly, I draw it like fully just 3 hexagons, and then I add in the nitrogens later. From there, I know on the left ring we have 2 methyls. On the middle one, we have a top and bottom nitrogen. And our right one, we have 2 amides. And so one of the nitrogens is up top, and then double bond O. One of the nitrogens on the other side, double bond O down. This left one is a fully just a benzene ring. And then for the other double bonds, I think about this as being part of a kind of a diagonal here. So like we have these and these here. And I just think that when you were drawing this, it's really easy to like put bonds in the wrong spot. And so just this is the way I go about doing it. And you'll see it when I draw one of the mechanisms. So, flavins, again, she's a little bit more complicated. She also is the star. So, flavin, FAD, she is going to be regenerated in every reaction. If we go back to NAD, we saw NAD, once we used it, it was done. It turned into, like, NADPH turned into NADP. And then we never reformed NADPH, right? Flavins, because they are like locked up, stationary in the enzyme, we need to reset them just the same way that we reset the active site for like a catalytic triad. So we would say that this is a redox catalyst versus like NAD and NADH just being used up. So I made a cheer to help you remember this. And let me see if I remember it. Okay. FAD is a catalyst. NAD is used up. FAD is a catalyst. NAD is used up. Can you try doing it? Do you want to try doing it with me? So, I'll do it slower. 1, 2, ready, go. FAD is a catalyst. NAD is used up. FAD is a catalyst. NAD is used up. So, it is, again, this kind of, like, bossier version, more complicated version of NAD. And you are not allowed to finish your reaction without reforming FAD. The joke I made when I taught this initially was, the stream ends when FAD regenerates. The stream cannot end until that happens. You cannot go on from the problem. The product oftentimes will be a distraction because reforming FAD can sometimes take a lot of steps, especially in some of the harder FAD mechanisms. So, you're going to learn 3 main types of FAD enzymes. The first type is called a reductase, and that's the type that you saw in lecture 5. And then the other two types, I believe you're going to see later. Again, I don't know exactly. Typically in like the Harvard College Chem 27, they do oxidases and monooxygenases. I think y'all are going to do them. I just don't remember what Serenia said. So I believe you are going to do these later. But we will start off with the first type, reductases. Any questions about structure function things for FAD before we get into reductases? Work. Okay. So, what's the purpose of a reductase? To reduce a substrate. And this is going to do a reduction that's very similar to NAD. So our general reaction here is we're going to go from a substrate at some oxidation level with carbon to a product reduced by one oxidation level. So here I just gave an example of like a ketone to an alcohol, but it can be whatever. We are going to have FAD in the active site, but remember it's a catalyst, it's not used up, so we're not going to do kind of an arrow. And then we are going to use an NADH or an NADPH to activate our FAD. Now you might be like, Colton, why don't we just use the NAD to reduce our substrate and not involve FAD? And I would be like, student, that's a great point. It feels kind of wasteful. It's just not what nature does for these. Nature has done this. I can't explain why nature does it. I am just here to say what nature does. Yeah. I was trying to even venture a guess of why we do this. Maybe I'll think about it while I'm talking through the general mechanism and see if I can come up with any ideas. So the general form for all of the FAD reactions, I glossed over it over here, is we are going to split up every FAD reaction into two half reactions. And I think it's really helpful actually on your notes to label them as reaction 1 and reaction 2. Just to make sure that you have it clear of this motif that's going to happen in every one of the FAD mechanisms. So the first thing that you do is you're going to go from FAD to its activated form FADH-. And that happens again every time. The second half reaction is FADH- can do a bunch of different things. But at the end of the day, you need to turn the FADH- back into FAD. So with these two half reactions in mind, we essentially have to activate FAD to make it FADH-, and then FADH- can do something. So our reaction 1, we are going to use our NADPH or NADH to reduce FAD. What that looks like is a typical NAD reduction here. And we are going to drop this hydride on the bottom nitrogen opposite of our little squiggle FAD abbreviation. When we do that, we're going to push electrons up and over to this top nitrogen here. So this is going to be the main thing that changes on your FAD each time you write it. So really nothing else outside of this kind of little squiggle is going to have different kind of bonds or added hydrogens or whatever. So when we do this and we add the H, now we are at FADH-. We have a negative charge on this top nitrogen because she already had one lone pair, and now we've given her a second. And then this bottom one has a hydride on it. Okay, so we've done the first reaction. We made our FADH-. Now FADH- can do her thing. And for a reductase, the FADH- just undoes what it did. So it's going to push down and now kick off a hydride and put it on a substrate. So when we do that, we get to our product and we reform our FAD. This one's not too bad because there's no way that we can form our product without also reforming our FAD. Another thing that I do with FAD mechanisms, just to keep myself honest, is I always mark when the reformation happens, just to make sure that we are doing it, because we know it's a structural thing that has to happen in every FAD mechanism. This one, again, is the easiest of the FAD mechanisms, and it's only 2 steps here, but it does feel kind of redundant, because, like, why couldn't we just have done this? We could have, but there are enzymes that use both of them together, and I didn't come up with a good reason for why. Maybe it's just to have another element of, like, control, like, because the FAD is bound in the active site, and the NADH or NADPH is, like, regulated at a cellular level, and it can, like, move around and be compartmentalized. Maybe that is why, just to have, like, an extra level of control. But here we are. So let's look at practice number 4 with this in mind. So, I can't pronounce this. Urocanate, sure, reductase, is a bacterial flavin-dependent enzyme that catalyzes the reduction of urocanate to imidazole propionate, shown below. Blah, blah, blah. What we see here is we are told that it has a flavin in it, FAD. We are going from, this bad boy seems to have changed and disappeared. Well, as a reminder, we know that, and this is a reminder if you've done 17, if you've done a different organic chemistry, you might not have seen this before. When we have an alkene next to a carbonyl, we know that there is actually resonance here, because all of these p orbitals can line up and spread out. And so this is often called an enone, E-N-O-N-E, and it's like an alkene and a ketone, basically. I know this is a carboxylate in this specific example. And enones, we can react to the carbonyl and do a carbonyl attack, or the other thing that we can do is we can attack at what we call the 1,4 position, right here. So this 1,4 position is another electrophilic site that's related to our carbonyl. So in general, what we have is some nucleophile could go and attack here, and we push all the way up to the carbonyl. Instead of attacking just directly at the carbonyl. Both are options, but I mention it because if you have not seen it before, this is going to look very weird. But what appears to have happened is it appears that we have added hydrogens to both of these carbons here. And if we think about it, this carbon is at oxidation level 1, right? Because it has an alkene here rather than a single. Actually, now that I'm saying that, it's like there's no bond to an electronegative thing. Why do we consider alkenes at a higher oxidation level? That's a great question. I have not thought through, and I'm quite tired. So I don't have a great explanation for you, other than to say that this is definitely at oxidation level 0 at the alkane level, whereas this alkene technically is at the alcohol level. I'll have to double check why. So with this, we are going to do our generic reductase setup. So we are going to start off with our reaction 1, and we start with building our flavin. So remember, we have 3 rings. Middle one has nitrogens on it, and then the other one is going to have 2 amides. And just getting this backbone takes some practice to get it all together. I'm going to form down the 3 rings. I have the 2 methyls on the end, and then this one is a benzene. And then I do kind of my diagonally double bonds here with the nitrogen in the middle. And then the top one connects up and becomes our abbreviation for FAD. Then we are told we have NADH, so I need to draw my NADH. Okay. And our first step is we are going to use NADH to reduce FAD. So we are going to push and restore aromaticity. The hydride is going to go and attack the bottom nitrogen. And then we are going to push up to the top nitrogen. So here, and this is the part where I'm not going to keep writing, I'm just going to copy and paste. So now we have moved our bond of electrons within the ring to the middle. We've added a hydrogen on the bottom, and we have a negative charge up top. So this now is no longer FAD, this is FADH minus. We've added a single H and a negative charge. And also, just by the way, because normally I think students are used to seeing FADH2, if this went and just grabbed a hydrogen, then that functionally is FADH2. So, like, this is kind of an equivalent of FADH2. We've just not added and removed the hydrogen each time. Okay. The other thing that we get out of this is a little NAD. Plus. And now, FADH minus, we've done our reaction 1, we are going to start our reaction 2, which is we need to have this interact with the urocanate. So I'm just going to abbreviate that ring as R, because we are not doing anything in our reaction with it. And now we know that we are going to push down and undo essentially the arrows that we did before and have a hydride attack. But do we want this hydride to attack at the carbonyl? Well, we still have the carbonyl in the product. So we are not going to go and attack the carbonyl. Instead, we're going to do this 1,4 attack and attack at the far side of the alkene. Boop. And then we are going to grab a hydrogen from something in the active site. Okay. When we do this, we are going to now have we added our hydrogen here at the bottom of our formerly alkene. And the other thing that we did was we regenerated FAD. Okay, so we seem close. The only thing that we need to do to actually get to the product from where we are is we need to add another hydrogen at, let me see, the other site that was in the alkane. So here we need to add another hydrogen here. And this is not technically going to be redox. This is just going to be acid-base. So over here, we are deprotonating this so that we can reform our carbonyl. And when we reform our carbonyl, we can grab a hydrogen from something in the active site. This functional group here is technically called an enol, and it's like an alkene and an alcohol. And enols can do this reaction where they tautomerize, is what we call it, and turn into carbonyl forms, ketone forms. And so we are at our product there. So let's see, did we have all of our hallmarks of an FAD reaction and of an FAD reductase? One, we had an FAD catalyst. We made FAD activated with FADH minus, and then we regenerated FAD. We reset the active site there. Two, what did we do? We used an equivalent of NADH or NADPH to reduce FAD and kind of activate it. So that got it set. I think those are the main features here. So, with that, I have like just a little bit more. And I don't have a ton of detail with it, mostly just because there, like the proline, there was one more thing that I just ran out of time for making, where a key example of the FAD reductases is glutathione reductase. And the reason why I waited until after the practice to do it is because glutathione reductase is a little bit weird. Like, it has a weird kind of reaction number 2, whereas like the standard general mechanism is actually kind of easier. So I thought I would show you a generic form, do this practice that's doing kind of a standard reduction, and then we could talk about the glutathione reductase. But before I do that, are there any questions with our general mechanism for FAD reductases, or this practice number 4, where we are reducing the enone?
For the arrow from the oxygen up to the like acid, would we do it to the oxygen and then do lone pair push up to the hydrogen, or can we do it directly from the double bonded oxygen, if that makes sense?
Yeah. And now that you mentioned that, that is the convention that Serenia uses. My bad. This is somewhat bad form of me. They used to not do that convention. They used to do it the way that I've done it here. But now they prefer students to go up and this attack, the lone pair attacks. And if I look at the key that is posted for it, or it's not posted, the key for it, they do show it like that. Let me check my other carbonyls to make sure I make that consistent. Yeah, like over here, I should change this as well. It's not my favorite abbreviation, mostly just because it adds arrows, and I don't feel like it is... like, both ways, there are abbreviations of things that are happening, but I think that they do want specifically that version. Do I have it anywhere else? Oh, literally every reduction that I did. Give me a minute, and I will go and fix those. Yeah. Yeah, woof. Over here in the answer key, they do have the nitrogen oxygen double bond going and attacking. But I do think that doing the convention is probably the better thing. Thank you for catching that, Fallon. Man, we did do that a lot in this lecture because it is redox chemistry. And it's also the thing, I was looking at the lecture notes, but my mind just was like, oh, that's the same. And again, they mean the same thing, basically. But did I do it in the other lecture, too? Yeah, I did it over here, too. I'll make a note for the future.
And when we regenerate FAD, can we just like write the letters FAD instead of redrawing it, or do we always have to redraw it when it's regenerated?
I do fear you always have to redraw it.
Oh,
I know. I know. Well, I mean, it's like the active site always redrawing it. Like even this, where I'm like doing this, feels a little bit cheap. I don't know if they would let that like slide on the exam or not. If I was grading it, this very clearly shows structurally this is the product, and it shows this regeneration in the catalyst. But I think that the safest option is to actually redraw the FAD, which sucks. I'm so sorry. Yeah, hate giving bad news. Any other questions or any other inconsistencies noticed with the mechanisms? Apologize for giving, having so many errors. Again, it's my first time teaching all of this, and so it's still working out some kinks. Okay. Well, with the last few minutes, I'll just give an overview of the glutathione reductase. So, glutathione is a free tripeptide. So it's made of 3 amino acids that exist in the cytosol of cells. It acts as a reducing agent, namely to get rid of molecules called reactive oxygen species. Reactive oxygen species are exactly what they sound like. They are forms of oxygen, O2, that are more oxidized and are thus more reactive. And they can like mess up your DNA. They can add oxygens to things that don't need oxygens or want oxygens. And so, glutathione, the structure of it is 3 amino acids. So we have a glutamine, or sorry, not glutamine, a glutamate that then, instead of making its dipeptide bond with the amino or the carboxyl group in the base of the amino acid, it makes the peptide bond here with the side chain. Like this is our R group 1,2 carbonyl. It uses this carbonyl for the like glutamate residue to form the peptide bond. And when that happens, we call this a gamma glutamate, because we are adding at the, we said this is the alpha carbon, beta carbon, gamma carbon, that's delta. I don't know why they do it gamma glutamate. Wow, I'm just running into like all of my things that I don't know today. But essentially it's glutamate, and we need something to designate that it reacts at the end over here, not the backbone. Then we have a cysteine, which I've deleted a carbon. What am I doing? What am I doing? Followed by a glycine at the C-terminal. So a tripeptide here. And then what happens is when it interacts with the reactive oxygen species, 2 of these glutathiones essentially get glued together. And they get glued together and form something called glutathione disulfide here, where it makes this disulfide bond between them. And I'll add the bond here. And we can abbreviate this as GSSG, just to not have to write everything over and over. So GSH, glutathione, GSSG is the glutathione disulfide. And then the enzyme glutathione reductase, its job is to go from this reduced form with the disulfide bond back to glutathione. And it again uses FAD in the active site and utilizes an NADPH to activate FAD. So the first step of it is exactly the same as all the other reductase steps of we do this reduction and generate an FADH minus. But then from there, it's a little bit weird. So I'm going to copy and paste this FADH minus, and I'll draw through that part of the mechanism that's a little weird. Boop. So, our FADH minus, in the second reaction here, once we have made the FADH minus, we are trying to reduce this disulfide bond and the glutathione disulfide, but the FAD does not do it directly. Instead, what the FAD does is it reduces a different disulfide bond that is in the active site. Now, again, you might be like, Colton, well, if it can reduce a different disulfide bond in the active site, why doesn't it just reduce the disulfide bond in glutathione disulfide? At which point I'd be like, that's a great idea. That's a great point. It just doesn't. So what it does is, this is step 2 here. The FADH reduces the active site disulfide. We have active site disulfide. We push down from FADH minus, then the hydride from one of them attacks one of the sulfurs in the disulfide bond, and then the other sulfur grabs a hydrogen from a general acid. When this happens, we reform FAD, which again we should draw, but for space I'm not right here. And what we generate is 2 active site thiols. I'll call them free cysteine residues. They are thiol functional groups. Then from here, the free cysteine residues interact with the glutathione disulfide here. So this is our GSSG. And from here, we have some acid base help with us. So a base deprotonates one of the free cysteines. The free cysteine is going to go and attack one of the sulfurs in the disulfide bond. And then it breaks that disulfide bond and it grabs a hydrogen from the general acid. And the last step here, so we've now made another disulfide bond. We've gotten messy in our active site. We still have this free cysteine. And then we've released one glutathione. So this is one GSH. Now we just need to release the other one. And so we do this same process of kind of a double attack. So now this cysteine goes and attacks the other cysteine, releasing our second glutathione. And what we get at the end of all of that, let me see space-wise where I can put this. Is we get another glutathione that's released. And we get our enzyme active site disulfide reset. So that is a reset of this active site. And I'll do some color coding here to help try to make it all together. So the active site disulfides are in this light purple. The glutathione I will do in blue here. And we had this for the disulfide glutathione, and now we have the free ones. So it seems like a lot of work. It's a little just kind of complicated in terms of how we break a disulfide bonds. Even in organic chemistry, we had to do this kind of double attack here for breaking disulfides. But you can see how, like, this part of reaction 2, we are using FADH to reduce something. It is doing, like, okay, it forms FADH minus first reaction, second reaction, FADH minus attacks something, and then we make FAD. But this is, like, way more complicated and a lot of kind of specific steps. I don't know that you actually have to have all this completely memorized for this class. I think it is a example that is like a hallmark example. Glutathione reductase is a very common enzyme active site. And when you're doing chemistry specifically of disulfides, it is a great example to have. But it is a little bit more involved here. So we have the step 2, FAD reduces the active site disulfide. And then we have step 3, the active site disulfides oxidize glutathione. What am I saying? No, they reduce glutathione disulfide. Fallon, yes, I just word vomited. Please ask questions.
Does the order matter? Because on the lecture notes for this, I think on page 26, they don't pull from the hydrogen, but it goes like from the double bond to the sulfur.
Huh. So then, but on the next page, 27. Oh, for that first step. Dang, I'm out here making mistakes. Yeah, the first step, you're totally right. It is a little bit weirder than that. Thank you for catching that. I'm so sorry. I'm going to fix it really quick. I know I'm going a little bit over. I was only looking at the next page. Wow. So we have FADH minus here. We have our active site disulfide, and we're going to have one more additional step here. So I was treating it much more like an NAD mechanism. But what happens here is our bond is going to go and attack this sulfur directly, and we're not going to just add the hydride to it. When that happens, I'm going to copy and paste this. We get a covalent adduct that is formed. Where now this is connected to one of the active site sulfurs. The other one is free. And from here, a general base comes in. Maybe my failure here is a lesson that these mechanisms are not the most straightforward in terms of what they are doing. Like, you could very easily think of something that chemically makes sense, that is not what happens. It is taking kind of 2 steps to do what you could draw arrows to do 1, but this is what is happening. It does make a covalent adduct with FADH. And then from here, we have the 2 free active site cysteines. Thank you so much again for catching that, Fallon. I appreciate it. Other questions on this, and then I'll be done. Again, sorry for the mistakes in this. This is what I get for not writing it out in advance.
Would it also be the same for the reaction we did previously, or is that a different case? I mean, it would still proceed the way you had drawn it.
You mean this one?
Yeah.
So for this one, I'll double check the answer key. No, this one, it just has the hydrogen attack directly. And again, I think it's the thing with specifically disulfides. Disulfides, it's really common to have this like dual reaction that like seems like you could do it in 1 step, but it takes 2. But like this is a very valid thing to happen for a hydrogen to go and attack. which is again why I wanted to do this generic version before I did the glutathione reductase version, where we make this covalent adduct. In the other FAD mechanisms that you're going to see later, the oxidases and monooxygenases, you are going to see more covalent adducts happen at this site right here. That's going to be kind of a key thing in the next section and the next lecture. But typically it's with oxygens, and we'll have like oxygen-oxygen bonds with like a peroxide or an O2. So like this is something that happens a lot, but this type of reduction is also totally valid.
Okay, so the covalent adduct should only be used when we have like the sulfur-sulfur or like in the future like an oxygen-oxygen, and then otherwise we can do what you have here.
Yes.
Gotcha.
And or if they say something about the active site specifically forms a covalent adduct between blank and blank, you know. But if they do not say, you can assume that you can do this rather than the covalent.
Gotcha. Thanks.
Yeah, no, thank you for calling it out. I really appreciate it. But we've gone long. I will go ahead and call it here. Thanks for bearing with me. I know that this is a long, kind of tedious section of a lot of material. And also it was just like a bigger undertaking, kind of pulling all the threads together. But hopefully this will help for some of the PSET stuff. We're going to take a break for a few minutes, and then we'll come back and do help room and talk about PSET things. So thank you for coming to section. I appreciate y'all.